So my name is Truman, Jian. I'm in the EC 2T3. So I was very fortunate to find work with a EC professor this summer, and I'm quite grateful for that. So the topic of our research is based on some new data structure that indexes regular expressions. So I'll just quickly go over all the gist of the problem. So what we have is a set of regular expressions inside our database. So a bunch of regex, and then we have some query string. And the goal is to have that query string to quickly identify all of the matching regex in the database to the string. So we want to quickly scan over and take all the accepting regex in the database and return all of the accepting ones. So this problem generalizes the publish and subscribe matching problem. So I'll just quickly go over the idea of this regular expressions regex. So for those who are not familiar, regex, regular expressions, is a string that's used as a pattern matching tool. So it's essentially a tag used to identify certain strings. So there are essentially four main operations in the standard regex language. So not the extended Unix where you have different types of you have extended functionalities, but essentially you have concatenation where you append different characters. So for example, A followed by B and D. A clean star meaning that the previous symbol can appear as many times as you like. So for example, this A can appear any number of times. We can also have a union here where we separate these two into two distinct groups here. And finally, we have a parentheses, which indicates this grouping order. So I'll just quickly go over the matching patterns for this. So what we have here is ABD matches this expression as we have one appearance of A, B, and a D. We also have ACD that matches, so we're going through this side of the group. We're going on the right side, so ACD matches this. And we have AABD, which, as I said earlier, was the clean star. The A can appear any number of times. Strings do not match is BAD. As shown in this diagram, the B only appears on the left side of the union operator, while the A appears on the right side, so therefore it does not match. And essentially, it's closed under some alphabet. So alphabet is essentially the set of acceptable characters inside our regex language. So I would like to quickly explain what it means by this publish and subscribe versus the query and retrieve. So the problem that we're working on is the publish and subscribe, where we take in one query input event, and we want to find this whole set of subscriptions such that it matches this input query event. So in our case, we have a one sentence or a string, and we want to go through the database and to find all the regex that matches it. Where on the contrary, we have query and retrieve, where we have this single regex expression, regex, and we're looking through this entire database for all the acceptable strings. So our problem is, given a one sentence or string, find all the regex in the database that matches this string. So there are many applications of regular expressions, in fact, one of them being for BGP routing, so determining round packet priority at different exchange points. Network admins can also use these regex to set up a list to diagnose different faults that occur within the network. We can also have personal advertising, which just means giving each user profile a set of tags such that when there's some string that identifies some object, some entity, such as close, for example, it quickly goes through all of the customers who have tags that allow it to match to the input string close. And of course, regular expressions are used mainly in XML processing. So we have filtering, routing, classification based on document tags. And finally, regular expressions form the basis of grep and egrep. So essentially any sort of tool that allows you to search certain strings or certain search certain strings or keywords within a page. So usually computer scientists use something called automata to represent these regex. So what an automata is essentially a computing machine that's derived from the regex. So there are two main types of automata. We have a deterministic finite automata and a non-deterministic finite automata. And what I mean by finite is because there are a finite number of states that this machine can be in. So here's this one implementation of what automata can look like. This one is being a graph. So what we have is nodes determining certain states, and we also have different arrows indicating transitions based on specific characters. So I won't really go over the notation, but I'll just quickly tell you what a DFA is. So a DFA means that every time we have an input, this automata can only output one certain state at once. So at any time during this processing, this automata can be only in one state at once. So this is what it means by deterministic. And a non-deterministic finite automata means that at any given iteration, we can have this automata be in multiple states at once. For example, we can be in both Q0 and Q1 for the input at the next iteration. And as a result, we have multiple states transitioning to another set of multiple states. So essentially, we're mapping one set of states to another set of states through each transition. So here's some backend code just to show how it works. I won't really go over it, but there's just two main ways to do it. One of them being a NFA, one of them being an epsilon FA, which is just a variant of the NFA, but essentially it completes the same task. So identifying a naive implementation of our research goal. So as I said earlier, we have a whole database of regex, and we have an input string, and we want to find all matching regex to it. So this naive way would be doing a linear scan over it. And as we see, the time complexity would be something like like the worst case time complexity to match one single string with a single regex, and multiplied by how many regex are there in the database. So essentially, I did some benchmarking here with some simple test cases here to show the extent of the naive implementation. So right here, we have this in case for it. If you see on the upper right corner, over here, we see that it takes about 33 microseconds to accept this single string. So if we have 1 million, if we scale this up by 1 million or something, this means that it would take 33 seconds just to find 1 million regex that accepts this single string. So obviously, this is not good and unacceptable, especially in the age of big data, because due to the Internet of Things, right? Like we have so many new devices and it generates rapid and exponential amount of data. So as a result, we need quicker algorithms to process to quickly crunch in these numbers. So essentially, we have 33 seconds just to scan over a database of 1 million of these regex. So that's not good enough. So this is where our research motivation comes in. So essentially, we're drawing inspiration from another data structure called R trees, a region tree. So what this region tree does is take different rectangles that classify such different entities. So the larger the rectangle is, the more general this entity is. For example, if we see in this diagram, we see that R6, within R6, there's rectangles R15 and R16. And R15 and R16 are bounded within R6, meaning that they're more specific and R6 is more generalized. And as a result, we use this to quantify and classify different sets of entities for a faster querying and search process. So as a result, we just need to descend down different levels of the trees, reducing the time complexity to something within the logarithmic time. So an example of this data structure is applied to postal code. So this is the map of the United States. So I'm not sure how the United States postal code system works, but I can guarantee you that these rectangles, the larger rectangles, contain a more generalized set of criteria that define some postal codes. And as we go into smaller rectangles, it becomes more specific until it gets to the individual household, which are the individual entries of this data structure. And some operations that this must contain are insertion, deletion, and so forth. So using that as inspiration for our data structure, we are proposing, well, we're building on top of it, and we're changing this into a regex tree. So what this regex tree does is take this query string, and we also use the property as from the rectangles analogous to rectangles, bounding rectangles from the R tree. We're using different regex to be the analogous to the rectangles. So as we descend down this data structure at the bottom, it will contain the individual entries of the data structure, the individual actual regex. While as we ascend the different node levels, we get a more generalized set of regex to define its children. So this is our motivation. So the R tree acts as our motivation for our current data structure, the regex tree. So there are many problems associated with trying to actually classify and make these like bounding automata, these bounding regex automata to classify different sets of RE. So one of them being that this problem is actually NP hard because we're essentially trying to split up this set of different REs into different nodes, right? Such that the pairings and the overall, such that the overall rectangular sizes are minimal. So that would be also an NP hard problem as it takes exponential time to do it. So actually most of the work that we do here is using heuristics to try to lower that time down to something that's more feasible. So for those who are familiar, this is a quadratic split here. We also have a different algorithms that generalizes. So this algorithm here, this generalized FA, it generalizes this set of automata. And when we choose some automata, a node to insert our new regex, we usually choose the one that leads to minimum expansion, which in other words, we try to find the one that has some greatest intersection with the current regex or automata that we're inserting. So this work was originally done in 2003 by another group of computer scientists, but my professor tells me that this work hasn't really been continued, so that's what he's quite interested in, especially with like the new computing technologies. He wants to further optimize and see if we can get like a better ratio over those over the scientists who worked on this in the past. So as we see, this RE tree works about 2 to 20 times faster based on a sample size of regular expressions from 500 to 2,500. So I'm just going to quickly talk about further development for our project. So what we have here is on a GitHub repo. So we want to first complete, because this data structure is still in developmental stage, right? We're almost done, so we want to first complete that. We also want to compare our results with the authors of the authors who actually did this experiment in 2003 to see if we can do better than them. And also we want to optimize our code for distributed and parallel computing, as my professors are quite into that field. And also my professor may want to try to look up new heuristics that computer scientists may have found that over the years coming up to this. I'd like to thank you for listening to the presentation. I'll take any questions right now.
Yeah, so thank you, Truman, for your presentation. And judges, if you want to unmute and ask your questions now.
Hi, Truman. So the retree concept is it's not new. It's been proposed in prior work as a way of sort of it looks to me like a sort of divide and conquer approach to handling regular expressions. Is that a correct sort of interpretation?
Yes. Yes. As I said before, this work was already done in 2003 by other computer scientists, but my professor, because our computing technology has vastly improved over the years, right? My professor wants to further optimize this data structure. And also, he wants to propose new heuristics that would give us an advantage over the work of previous scientists.
Okay.
Any other questions?
But so far, your specific work, it looked like from your talk today, it wasn't exactly clear what your, sort of what is the novelty of what you've done. I mean, it's great to learn about all this stuff, but is there something you want to point to there about your own contribution above sort of what was previously in the literature?
Yeah, so this project is actually quite new. My professor only took interest about 2 months ago over this summer. So right now our first step is trying to first replicate the results from before we start doing implementing our own features. The direction of that is not known right now, but I hope to